All right, get ready because today we're going deep into AI.
Deep but tiny.
Yeah, that's right. We're going to be looking at this tiny neural network.
That's right.
It's so small, it just tackles this basic logic problem, the XOR gate.
Exactly. The one that only outputs true.
Right.
When just one of the inputs is true, not both.
Yeah, and for this deep dive, we've got this paper from Yang, Aurora, and Bachman. It's called Dissecting a Small Artificial Neural Network.
And of course, we've got some background material on the history of neural networks.
And a study guide with some quiz questions, in case you want to test yourself.
Oh, nice.
And even some FAQs that give us some more insights into the paper.
So basically, we're going to dissect this tiny network and see if it can tell us something bigger about how AI learns.
Sounds good. So where do we even start with this whole XOR thing? I kind of remember it from, back in the day, my computer science days.
Yeah, well, the XOR gate was actually a big deal in the early days of neural networks. Way back then, we had the perceptron, one of the first neural network models.
Oh, yeah, the perceptron. Wasn't it supposed to be revolutionary?
It was promising, but it couldn't solve the XOR problem. Actually, this led to what we call the first AI winter.
Oh, wow. So this simple XOR gate actually stopped AI research.
Kind of, yeah. Because the XOR problem, it's not linearly separable, which means you can't draw a straight line to separate the inputs that give you a true output from the ones that give you false.
Okay, starting to see why this is tricky. So how did researchers eventually get past this?
They realized they needed networks that were more complex, which brings us to the little network we're dissecting today.
Okay, so explain this minimal XOR network. How's it structured?
It's got two input neurons, a single hidden layer with two neurons, and then just one output neuron. Simple.
Sounds deceptively simple. And I remember from the paper, there are 9 parameters that have to be tuned for this thing to learn.
That's right, weights and biases. These are really important because they control how information flows through the network.
Can you break that down a little more? I'm a little fuzzy on weights and biases.
Sure. So think of each connection between neurons like it has a certain strength.
Okay.
Like a dial that can either amplify or dampen the signal going through. Those are the weights.
So the weights say how much each input matters to the next neuron.
Right. Now, the biases are like thresholds. They shift the activation function of each neuron and basically decide how easily it fires or sends a signal to the next layer.
So biases control how sensitive a neuron is to its input, kind of like setting a thermostat to decide when the heat turns on.
Great analogy. And then we have the activation function. In this case, it's the sigmoid function. That's what gives us the nonlinearity we need to solve the XOR problem.
Right. The sigmoid function takes all the weighted and biased inputs and spits out an output between 0 and 1, which basically represents false and true.
Exactly. So we've got our network, our weights, biases, and our activation function. But how does this little network actually learn?
That's where backpropagation comes in, right?
Yeah, absolutely. Backpropagation is the heart of neural network training. It's how the network learns from its mistakes.
Sounds almost human, learning from trial and error.
In a way, it is. It's a repeating process. First, the network gets a set of inputs, those XOR cases we talked about.
Then it compares its output, its guess, to the real, true output using a loss function.
Right. The loss function measures how far off the network's prediction is. Then, using this loss value, backpropagation adjusts those weights and biases just a tiny bit, trying to reduce the error with each iteration.
And the paper talked about them testing other optimization methods besides the standard one.
Yeah, like the atom optimizer, that can really speed things up. But the basic idea is still the same, tweaking the weights and biases to get closer to the right answer.
You'd think learning would be pretty straightforward for such a small network, wouldn't you?
Well, not exactly. The researchers actually saw 3 distinct phases in how the network converges. That is how it gets to zero loss.
Okay, I'm intrigued. What are the phases?
Well, the first phase has some fluctuations in the loss, like the network's trying different things out.
Right.
Then there's this sudden drop in loss, like it's found a good path and is moving towards the solution really fast. We call that the attraction basin. That's where the learning rate comes in, that parameter that controls how big the adjustments are.
Right, so a higher learning rate means bigger steps toward the solution.
Right, but be careful, too high, and you might miss the target completely.
Okay, so after the exploration and the quick descent into the attraction basin, what happens next?
The network enters this long-term phase where convergence slows down and follows a power law.
A power law, like those math things that describe gravity and stuff?
Exactly. The loss keeps decreasing, but slower and slower. And get this. The researchers found the weights and biases keep changing even after the network reaches a low loss.
Hold on, so it keeps learning even after it basically solves the problem.
It's not about finding one perfect setting for the weights and biases. There's a whole range of solutions that all lead to near zero loss.
So multiple paths to the same answer. Interesting. But how do we even picture this with 9 dimensions?
That's where the researchers get clever. They use this really cool analogy, the loss landscape.
I'm listening.
Imagine this big mountainous area where each point represents a different combination of those 9 parameters, and the height at each point is the loss value.
So the network is trying to find the lowest point on this landscape, the valley of zero loss.
Exactly. And the paper's analysis of this loss landscape revealed some amazing features that directly affect how the network learns.
Like what kinds of features?
Well, for that, you'll have to stick around for part 2 of this deep dive. Welcome back to our deep dive into this tiny neural network.
We left off with this idea of the loss landscape, that 9-dimensional mountain range that has all the possible settings for our network.
Right. And as we said, it's not a simple hike to get through it.
Yeah, it's more like trying to get through some crazy wilderness.
That's a great way to put it. Even with just 9 dimensions, those 6 weights and 3 biases, the loss landscape is really complex.
So how do they even map this thing out?
Well, they look at cross-sections, basically slicing through those 9 dimensions to see how 2 parameters relate at a time.
So instead of this 9-dimensional mountain range, they're looking at these 2-dimensional slices.
Exactly, and they found that these slices are full of features that really affect how the network learns.
I'm picturing like cliffs and ravines and secret paths and huge plateaus.
Yeah, exactly. And they found these features at specific loss values 0, 0.25, 0.5, 0.75, and 1. These correspond to how many of the 4 XOR cases the network is getting right.
So at a loss of 0.25, the network is getting 3 out of 4 of the XOR cases correct.
That's right. Now, around that zero loss point, that global minimum, they found a well-defined, even trenches sometimes leading toward it.
So the network might get lucky and fall right into this well and find the best solution right away.
But it's not always that easy. The worse the initial loss, the harder it gets. It's like the network wants to get to that valley floor, but might get stuck if it makes a wrong step.
So even getting close to a good solution doesn't mean you're going to succeed.
Yeah. And as you move away from that zero loss point, the landscape gets even more complicated. They found channels, which are these paths of low loss that can lead the network to better solutions.
These channels sound promising.
Yeah, but then there are barriers, areas of high loss that act like roadblocks. These trap the network in a local minimum and stop it from getting to that global minimum of zero loss.
Like hitting a dead end in a maze and having to go back to find a new path?
Yeah, the fact that these barriers and local minima exist just shows how hard it is to optimize neural networks.
So it's not just going downhill, is it?
Not at all. Sometimes the network has to take a roundabout path, even going uphill a bit before it can find a better way down.
And then there are those plateaus, right?
Yeah.
Those big flat areas where the loss doesn't really change much.
Exactly. Imagine being stuck on this huge plane, no idea where to go. It would be pretty discouraging.
It sounds like they could really slow the learning down.
Oh, they totally can, even if they eventually lead to the right solution.
So we've got wells, channels, barriers, and plateaus all affecting how the network learns. And this is all in 9 dimensions, and we're just talking about a simple network.
Imagine the complexity for a network with millions or even billions of parameters.
It's crazy. But even with this simple network, we can see that training AI, even for a basic task, is really complex.
It really is. Now, another thing the researchers looked at is how the order we give the XOR cases to the network affects this landscape. They compared randomized versus non-randomized batches of the input data.
Remind our listeners what those batches are again.
Okay, so during training, we don't show the network all 4 XOR cases at once. We use batches, smaller groups of the data to calculate the loss and update those weights and biases.
It's like showing the XOR cases to the network on flashcards, a few at a time.
That's a good way to think about it. A non-randomized batch would always present the XOR cases in the same order, like going through those flashcards in the same sequence.
And a randomized batch would shuffle those cases so the order is different each time.
Exactly. You might think that randomizing would totally change the loss landscape.
Yeah, it makes sense. Different input order, different calculations, different adjustments.
But here's the surprising thing. Even though each run with a randomized batch looks different, if you average all those landscapes together, it looks almost exactly like the one you get with the non-randomized batch.
Wow, so even though each run with a randomized batch looks different, the overall picture is the same.
Right. And this is really important because it means using randomized mini batches in training large networks, which we do a lot because we can't use all the data at once, is a valid approach.
So even with randomization, the network's still dealing with the same basic loss landscape.
Now, remember how we talked about using physics to understand how AI learns? This is where it gets super interesting.
I'm ready.
The researchers use this idea of microcanonical entropy, which is a measure of disorder or randomness, to analyze our tiny neural network.
Hold on, entropy. Isn't that from thermodynamics, like the arrow of time and all that?
Exactly. It's a concept from physics, but it turns out to be really relevant to AI too.
Okay, I'm curious. How does entropy relate to a neural network learning XOR?
Okay, think of the network's learning like annealing. It's like heating up a metal and then cooling it down slowly to make it stronger and get rid of defects.
So the network starts with high entropy, lots of randomness, and as it learns, it goes to states of lower entropy, becoming more organized.
Exactly. And they found that the entropy was highest at a loss of 0.5. That's when the network is getting half the XOR cases right and half wrong, a maximum uncertainty.
So high entropy means high uncertainty.
Right. And as the network learns and the loss decreases, the entropy drops. That means the network is getting more organized, less random.
So learning is going from chaos to order.
I like that. But here's the really cool part. The shape of that entropy curve actually matches the features we see in the loss landscape.
You mean those barriers and plateaus?
Yep. Those areas of high loss in the landscape, they match up with areas of high entropy where the network's learning slows down.
It's amazing how these ideas from physics can help us understand what's happening inside the network as it learns.
It's like we're looking at the learning process under a microscope.
This is all really insightful, but I'm still curious about something you mentioned before. How does changing the number of hidden neurons affect this learning process?
That's where we'll pick up in part 3.
Welcome back to the deep dive. We've been on quite a journey through this surprisingly complex world of a tiny neural network learning to solve the XOR gate.
Right. We've gone through this whole loss landscape, those tricky barriers and plateaus, and even used entropy to understand how the network learns.
And now the big question, how does changing the number of hidden neurons in the network affect this whole learning process?
It's a really good question, and it gets to the core of how we design neural networks.
Because remember, we started with just 2 hidden neurons, which felt like barely enough to even solve the XOR problem.
Right, and the researchers actually took this even further, going all the way up to 18 hidden neurons.
Wow, that's like 9 times more complex than our original network.
Yeah, and what they found was that by calculating these microcanonical entropy curves for bigger and bigger networks, there was this interesting trend.
What happens to those curves when you add more neurons?
They smooth out. Those sharp peaks and valleys we saw before those areas of high entropy, they get less extreme as the network grows.
So those rough spots in the loss landscape become more like gentle hills.
Exactly. Adding more hidden neurons makes the path to learning smoother.
So it's not just about having enough neurons to handle the problem, it's also about how efficiently the network learns.
That's it. Adding more neurons gives the network more ways to find those good solutions, those low loss areas.
It's like giving the network more tools to work with, making it more likely to find the right answer.
Exactly. And this is important for designing neural networks, especially in deep learning where we have tons of parameters.
So even if a larger network seems like overkill for the task, it might actually learn better and avoid getting stuck in those local minima.
There's a balance, though. More neurons mean more calculations, so it's about finding the right balance between complexity and efficiency.
Right, finding that sweet spot.
But the main takeaway is that the number of hidden neurons doesn't just change how much the network can handle, it actually changes the whole learning process.
Wow, that's really interesting. So let's take a moment to recap everything we've learned from our deep dive into this tiny neural network.
We've seen how complex it really is and discovered some fundamental truths about how AI learns even in the simplest of cases.
We started with the loss landscape, that crazy multidimensional world of weights and biases, and saw how it's full of obstacles and paths that shape how the network finds a solution.
We talked about how the learning rate affects things, how it can either speed things up or slow things down.
And we even went into physics and used this idea of entropy to see how learning is all about going from disorder to order.
It's like going from chaos to a clear solution.
Well said. But maybe the most surprising thing is that Adding more hidden neurons doesn't just increase capacity, it actually makes the whole learning process smoother.
And that's what's so cool about the deep dive. We took this simple neural network and found out so much about how AI works.
It shows that even in the smallest things, there's a whole world of complexity to discover.
And like our little network finding its way through the lost landscape, we're always on a journey of learning.
So keep asking questions, keep being curious, and keep diving deep into this amazing world of knowledge. That's it for this deep dive. Thanks for listening.